we can start. So good afternoon, everyone. Welcome to the second installment of our mini course on path integral approach to quantum mechanics and quantum field theory. You all met already our speaker, Dr. Sunandan Gangopadhyay, and we are very happy that he's with us again today, because last week he gave us a very nice lecture, and I'm sure you can't wait to hear how the story continues. So Sunandan,
yes, thank you.
You probably want to share the screen again.
Yes.
So you're welcome to do that. And I remind people to, and there are still people coming in, to make use of the Q&A to ask questions, and maybe at the end of the lecture, just raise your hand and we can give you the right to speak and ask the question in person. Yeah. Okay. So Sunandan, please, if you want to start, you're most than welcome. Yeah.
Okay. I should start probably now. So are the slides visible?
Yes. We can see them clearly. Thank you very much.
Okay. So in the last class, what I discussed was the formulation of path integrals in quantum mechanics. So let me just briefly review what I have already done in the previous lectures. So I've just gone back to the slide. So I discussed the time evolution operator and how it takes us from a given state gate to another state gate at a later time. So this is the time evolution operator, and I mentioned that for a time independent Hamiltonian, the time evolution operator is of this form. Then I showed a small result that if I call if I write down the time evolution operator in this way, then I derived a small result. I showed that if you take IH bar del L T2 of this time evolution operator, that is, differentiate this time evolution operator at the later time T2, then we shall land up to this equation. Which basically tells us that this time evolution operator is basically a Green's function, not really a Green's function, because this is not a function, this is an operator. This operator basically satisfies this kind of an equation, and so this is a Green's function like operator, because this operator, when it acts on this particular thing, gives us a delta function. So this is the thing that I discussed, and then I mentioned that how to determine this function is one of the main problems in quantum mechanics, and the main important thing that we are after is to calculate this following amplitude. So this is the base gate at some initial position Qi, and then you have this time evolution operator, and it takes you to QF, and this is in the Schrodinger representation, where base gates are time independent, state gates are time dependent, and operators are time independent. And this is in the Heisenberg representation, this particular thing, which is where the base gates are now time dependent, state gates are time independent, and operators are time dependent. So this is the thing that we have been after, and what we did in the previous lecture was to find out a path integral representation for this object, which is nothing but the overlap between Qi, 0 and QF, t. And we showed that this object is basically nothing but given by the following expression, the following path integral representation. So we showed that this object Qi, 0 and QF, t is given by this expression, and this is nothing but a sum over all possible paths in the phase space, which start from Qi, 0 and end at QF, t. So this is, we mentioned that this is the phase space form of the path integral, and from here we then went on to discuss the stationary phase approximation, and in that approximation we derived or what we basically did was to eliminate the momentum thing, and we went on to derive a configuration form of a path of the path integral representation for this object, where you now have only a path integration over these Qs. So this is sometimes called, or often called, the Lagrangian path integral or the configuration space path integral, which is the integral over all possible paths Qt in configuration space, weighted by the e to the power of I by h bar s factor, where now s is the Lagrangian action. We also discussed the classical limit, and then we went on to discuss the non-relativistic Hamiltonian. And the non-relativistic Hamiltonian is of this form. If we take a Hamiltonian of this form to be p squared by 2m plus some potential v of q, so this is a non-relativistic Hamiltonian. And if we choose this form of the Hamiltonian, then this we showed that the phase space form of the path integral can be now the momentum functional integral in the phase space form of the path integral can be now done exactly, because it is basically a Gaussian integral, Gaussian functional integral in the momentum. So you can do the integral exactly. And if you carry out the integral, we landed up to the once again to the configuration form of the path integral, where SQ is the standard Lagrangian. So it is basically LDT, integral LDT. So these are the things that we did in the previous lecture. And now today I start from here, because the next part I could not cover. I mentioned that it would be a good point to stop at this point. And today what we shall do is show how we can calculate the free particle path integral exactly. So for a free particle, we know that you can see that this is the Lagrangian. So this Lagrangian, you know that this is basically half m q dot square t minus v. So this is the form of the Lagrangian. And for free particle, we know that this v, the potential v, must be equal to 0. And let us see how we can carry out this path integral. So we set v to be equal to 0, and then we once again write down the path integral representation, which is the overlap of qi comma 0 with qf comma t. So this is the path integral representation, and we write it down by breaking it up. So this is actually the skeleton form of the path integral. So what we usually do, we write this skeleton in a compact form by introducing the notation, by introducing this fancy notation, which is this square brackets dq inside square bracket with qi comma 0 at the bottom and qf comma t at the top, and times this e to the power of I by h bar sq. What this basically means is that this is not an ordinary integral, this is a functional integral, which means that this s, the action, is a functional of this q, and now you integrate over all possible functions. So this is a function, that is why this is called a functional integral. But actually the real meaning of this functional integral is this thing. This is the actual meaning of that functional integral, and that is why I call it the skeleton form of the path integral. So if you break this up in this form that we derived earlier, now in this case you see the v term is not there. Therefore, since v is 0 for the free particle, so what we need to evaluate is just this integral. So you can see that this is nothing but there are infinitely many integrals. So there is an integral here also over this thing. So I should have written down the integral over here, and then there is an integral over like this. So there are infinitely many integrals. Actually, you can see that there are 1 to n minus 1 kind of number of integrals over q, but n tends to infinity. Therefore, actually, there are infinitely many ordinary integrals, and all the integrals are running from minus infinity to plus infinity. So that actually, so the integration, all these integrals running from minus infinity to plus infinity basically captures the fact that this is an integration over all possible paths. So that is why the name path integral. But so it may seem a very horrendous kind of thing, not a very nice thing to evaluate, because there are infinitely many integrals, with all the integrals running from minus infinity to plus infinity. So this is a very bad thing to evaluate. But the nice thing about this calculation is that, or one may think that it is a difficult thing, but it may be doable, because all these integrals, say the q1 integral or q2 integral, and then to q up till qn minus 1, all these integrals run from minus infinity to plus infinity, and all these integrals are Gaussian integrals. So this is the nice thing about this object. So one may think that since these are Gaussian integrals, so there may be a way to actually calculate this thing exactly. So one of the ways to work with this integral, this functional integral, is to work a few lower ones and then derive a pattern. Let us perform the q1 integral first. So from this expression, I just isolate the q1 integral and perform the q1 integral first. Let's see how it can be performed. So if you just isolate the q1 part, so it will be integral from running from minus infinity to plus infinity, integral over q1, so dq1, and then this is the integrand. So the q1 term will come from m is equal to 0. So m is equal to 0 will give one q1 term, because the m is equal to 0 term means this is q1, m is 0, so this is q1 minus q0, and all q1 term will also come from the m is equal to 1th term, because that will give us q2 minus q1. So there are two terms or two m terms from which the q1 can appear. So let us write it down. It will be e to the power of I by h bar epsilon m by 2 epsilon square, which comes from this factor. So I by h bar epsilon, and then you have m by 2 epsilon square. I've taken it out, and then you just write down the q1 part. The q1 part appears like this. It is q1 minus q0 whole square plus q2 minus q1 whole square. So this is the integral that we need to perform. The good thing about this integral is the following. If you just expand this out, you will see that this is nothing but a Gaussian integral in q1. Not really it is a Gaussian integral because it is quadratic in q1 square. But as I mentioned in my previous lecture, there is a catch here. The catch is that in usual Gaussian integrals, we usually have, let me just write it down here. I wrote it down earlier also. So in usual Gaussian integrals, you usually will find that it is something like e to the minus infinity, e to the power of minus a x squared dx, that is equal to pi by a square root, with the with the restriction that real part of a must be greater than 0. So what we are saying is that this small a can be a complex number in general also, but the value of this integral will be equal to square root of pi by a if the real part of a is greater than 0. Why the real part of a should be greater than 0? It should be greater than 0 because of the simple reason that this integral, only for this condition, the integral will give you a convergent value. Otherwise, it will blow up. So that is why you need this restriction. So here you can see that this integral, this a is a purely imaginary number. So you can per se, you cannot apply this result. Just by taking this result, you cannot apply this Gaussian integral, and you cannot say that this is square root of pi by a. But you can do a trick. If you want to know the trick, I can show you later. It is a very simple trick. You can actually do something which is called regularization. If you regularize this integral properly, then you can show that it once again becomes a Gaussian integral. And if you do that, the result of this Gaussian integral will be this. So you can see that there is some constant factor sitting in front times e to the power of this factor. So it is I. So this complex number is still there. And obviously q1 has been integrated out. So the only things that appear here is q2 and q0. And you will notice that I have written down this result in a very in a particular way. I have written down this constant here. I could have, so there is a 1 by square root 2 here. I could have put this square root 2 inside here. And then if I put this 2 inside here, this 2 and this 2 will cancel. But I don't want to do that. I want to write it in this form. The reason for writing this in this form without cancelling this square root 2 factor is very simple. As I mentioned before, I want to derive a particular pattern by evaluating a few lower integrals. So that is why I keep the 1 by square root 2 factor outside. And here also you will find that I have written it in a particular form. I have written it e to the power of I m by 2h bar epsilon, and then I have kept a 1 by 2 factor outside. I could have easily written it as I m by 4h bar epsilon, but I am not doing that. You will see the reason why. So now we have performed the Q1 integral. Let us now go ahead and perform the Q2 integral. So if you write down the Q2 integral now, so dq2, so Q2, again, you have to look into this expression and isolate the Q2 terms. And obviously, one Q2 term has come out by doing the Q1 integral. You see that Q2 is sitting here also. So you have to take this term also. So if you do that, then the Q2 terms that you have, that you need to integrate are the following, this one and this one. So once again, you can very easily see that this is a quadratic thing in Q2. So it is quadratic in Q2. So and that makes life simple, because you can evaluate this Gaussian. Once again, this is a Gaussian integral, and you can evaluate it by using the result that I've already written down. And the result is the following. I keep it as an exercise for you to check all these results, because this is trivial. What you need to do is just expand this out, complete the square, and apply this result, apply this Gaussian result, integral result. And if you do that, this is a very simple exercise. If you get stuck, you can ask me. I can show you in details, but this is a very simple thing to do. Please check it. And if you do it, you will get the following result. Once again, you can see that the constant that appeared here, the same constant once again appears here. I wrote it as 1 by square root of 2. Now I'm writing as square root of 2 by 3. And then in the Q1 integral, it was e to the power of this constant times half. Now it is e to the, again, the same constant, but 1/3 appears, and then Q3 minus Q0 whole square appears. So now the fact that we have performed the Q1 and Q2 integral, you can again go ahead and perform the Q3 integral, and you will see that a very nice pattern comes out from this thing. And the nice pattern that comes out is the following. You will see that you can write this down in the following way. If you perform all the n-1, so there are n-1 integrals now. If you perform all the n-1 integrals, you need to just keep in the mind that if you go back here, you will see that the skeleton form of the path integral had a constant a here, and that constant was given by this value. So you have to also keep into track the value of this constant. So if you keep into track the value of this constant, then and perform all the n-1 integrals. So what will happen? The interesting thing about this thing is the following. You see that now you can multiply this Q1 integral, the result of the Q1 integral, with the result of the Q2 integral. And if you do that multiplication, so now it means that you have carried out the Q1 and Q2 integrals. So if you carry out these two integrals, the result will be this constant to the power of 2. Right, because to the just this constant, because it is a square root of this constant and this constant square root. So if you multiply these two things out, it will just be this factor. So 2i pi h bar epsilon by m. And then when you multiply this with this, you will see that the factor of 2 and this 2 cancels out completely, and the resultant of the product of these two integrals will be just this constant multiplied by 1 by square root of 3 e to the power of this thing, right? Now, if you keep on multiplying, doing the higher integrals like Q3 integral, Q4 integral, and keep on doing till n-1, what will happen is that you can now write down the results in a simple way. This constant will appear. This constant was also already there. Now, this particular constant appears for each of the integrals. So now it will be multiplied n-1 times. So you will get 2 pi I h bar epsilon by m whole to the power of n-1 by 2, right? So this factor will come, this whole factor will come to the power of n-1, and you will see that all these factors that I had written down, this is 1 by square root 2, this is square root of 2 by 3. When you multiply all these factors out, what will remain is a factor of 1 by square root of n. And here also, if you just keep on multiplying these things out, you will find that finally you will find that it will be e to the power of I m by 2 h bar epsilon 1 by n qn minus q0 whole square. And when you just simplify this with this, you will see that it will be square root of n by 2 pi I h bar epsilon 1 by square root of n times this thing. And now you have to take limit epsilon goes to 0 and n, capital N, which is the number of time slices that I showed you earlier, the number of time slices into which you have divided the full time interval. This, in the limit of this going to infinity, you will see that something interesting occurs. You can put this square root n factor inside this factor. So this becomes square root of m by 2 pi I h bar n epsilon. And here also you have a factor of n epsilon. And if you remember that this n, the number of time slices multiplied by the width of each time slice, is actually the total time interval, and that is basically capital T. So this result in the limit epsilon goes to 0, n, capital N goes to infinity, becomes square root of m by 2 pi I h bar capital T e to the power of I m by 2 h bar T qf minus qy whole square, where I've just written q naught to be qy and qn is basically qf. So this is the transition amplitude for the particle situated at qi at the time t is equal to 0 to go from qi to qf at time capital T is equal to capital T. So this is the probability amplitude of transition and for a free particle, and the result is the following. You can see that this is a very nice result, and this is the result for the free particle. And you can make a very simple check. You can check that whether this, if you set this capital T to be equal to 0, then it basically means that this is the overlap of qi with qf. And the overlap of qi with qf is very simple. It is just a Dirac delta function. It should be delta qf minus qi or delta qi minus qf. And you can check that your answer that you have obtained by evaluating the free particle path integral exactly is consistent with the fact that in the limit t goes to 0, this overlap actually goes to the Dirac delta function. This is a very standard result. You take the t going to 0 limit of this result, it boils down to the Dirac delta function. And this is the orthonormality relation for states in the Heisenberg picture. So what we have now done is evaluate the free particle path integral. And I must mention that there are a very few cases in physics where you can actually evaluate the path integral exactly. Another important case where the path integral can be evaluated exactly, but I will not cover now, or maybe I will not cover it in this lecture, is the harmonic oscillator. The harmonic oscillator path integral where V, so let me just go back to the form of the path integral once again. So this was the form of the Lagrangian. It is half mq dot square minus V. So in the harmonic oscillator case, this V is basically, so where is my pointer now? See the pointer. Okay. So this, in the harmonic oscillator case, this is half m omega square q square function of t. So this is the harmonic oscillator potential. In this case, once again, the path integral can be evaluated exactly, and it gives a very nice result. And the reason that this path integral for the harmonic oscillator can be done exactly is very simple. Once again, you can see that for this form of the potential, which is the harmonic oscillator potential, the functional integral is once again a Gaussian functional integral, and therefore it can be done exactly. So in physics, whatever things that we encounter, if they are Gaussian integrals, everything can be done exactly. But if you go to higher order things, for example, if we try to solve the anharmonic oscillator term, where there is a q, where the potential is not only contains this q square kind of term, but also has an additional term such as q to the power of 4 or q to the power of 6 kind of terms, or q cube kind of terms, then the path integral can no longer be evaluated exactly, and one has to take recourse of perturbation theory to get some approximate answer for this path integral. But the harmonic oscillator, so far as the harmonic oscillator potential is concerned, you can actually evaluate this path integral exactly. But we will not cover it now because that is a very long calculation, and but we will cover some other things which are also quite important. But I urge all of you to please look at the harmonic oscillator case and try to solve the harmonic oscillator path integral yourselves. If you have problems, you can contact me later through email or whatever. You can ask me in the question hour session also. Now I shall go into something very important. This is called the imaginary time formalism. So let us consider the time evolution operator u hat t. So that I had already written down. And the time evolution operator u hat t is given by e to the power of minus I by h bar Hamiltonian operator h hat t. So this Hamiltonian operator, I'm assuming that this is time independent. Let us set this time t to be equal to minus I tau. Okay. So if you do that, if I set t to be equal to minus I tau, so what I'm doing is that I'm now saying that this time that I have here is not a real number, but rather it is a complex number. So this tau that I have here is a real number. So this t now is becoming a complex number. If this tau is real. So what I'm basically doing is I'm rotating my time axis, or analytically continuing the real time axis to the imaginary complex plane. So this time is now imaginary. So if you do that, you will see that this time evolution operator u hat t now becomes a function of tau, and tau is equal to it. And if you set small t to be equal to minus I tau here, then this time evolution operator becomes e to the power of minus 1 by h bar Hamiltonian operator tau. So no longer, so this complex number I no longer sits here anymore. And this would have been, you will see the consequence of this in a moment. This would have been the time evolution operator if the Schrodinger equation had been written in this form. Had the Schrodinger equation been of this form, then the time evolution operator for a time independent Hamiltonian would be of this form. A formula for u hat tau can be written down at once now. What you do, you still know that the eigenstates of this time independent Hamiltonian operator are ketens. So these are the eigenstates. So what you do is you just insert a identity operator here, right? So I can write down u hat tau, function of tau, as some identity operator, because these eigenstates of the time independent Hamiltonian, they form a complete basis, and therefore summation over n keten Bryan is equal to the identity operator. So what I have done is just introduce a identity operator here. So summation n keten Bryan, and then you have u hat tau here. And now I just put in the form of u hat tau, which is e to the power of minus 1 by h bar Hamiltonian operator tau, and you already have this particular thing. And now this h hat operator, see this n's are eigenstates of this Hamiltonian operator, and the Hamiltonian operator, we all know that it is Hermitian. Therefore h hat keten is equal to en keten. So you have this equation. These are eigenstates of the Hamiltonian operator. Therefore this h hat, which lies in the exponent of this, this also operates, when it operates on this Bryan, it will give you en. So now it becomes an eigenvalue, it becomes a pure number, and therefore the formula for u hat tau becomes summation over n keten Bryan e to the power of minus 1 by h bar en tau. It doesn't matter whether you write this e to the power of minus 1 by h bar en times tau on the right hand side or on the left hand side, because now no longer this is no longer an operator, it is a pure number. So you can write it anywhere. I've written it down on the right hand side. But the important thing is that you should be careful. You cannot just, at this point, if you write is equal to, this step is equal to e to the power of minus 1 by h bar en tau, that is not true, because summation n keten Bryan is equal to identity. But now you cannot no longer use this, you can no longer put this thing to be equal to identity, because n is also sitting over here. So you cannot apply the completeness relation now. So you should not make the mistake of removing this thing completely and write the result to be just equal to this. That would be a blunder. So you should keep this in mind. The main point from this short exercise is the following. The main point to note is that even though the time is now imaginary, so we have rotated the time axis, the real time axis, the eigenvalues and eigenfunctions that enter into the formula for u hat tau are the usual ones. So the same ketens of which are the eigenstates of the time independent Hamiltonian, and the eigenvalues of the time independent Hamiltonian h hat, which are en, those same things entered the formula for this new time evolved operator, evolution operator. So this is something important. Now, once again, we shall carry out the same exercise and see what is the status of the path integral, of the configuration space path integral. So once again, I rotate the real time axis. I set t to be equal to minus I t tilde. So if I do this, so now this t becomes imaginary because this t tilde is a real number, as I mentioned earlier. So this t tilde is a real number, and therefore t tilde can be written as it. Now at t is equal to 0, if I set t is equal to 0, then t tilde will be equal to 0. And if I set t is equal to capital T, then t tilde will be equal to it, right? So, so these are the limits that we have. So t tilde is equal to I capital T, and that I call to be equal to tau. So in this case, what I am doing is that for the particular case, I'm writing t to be equal to minus it tilde, but here there is a catch. What I'm saying is that now t tilde is basically imaginary, t is real, because I'm setting the limits t to be equal to 0 and t tilde t is equal to 0 and t is equal to capital T. So you just keep this in mind. And now I write down the overlap of x prime comma 0. I have just used a new notation x prime. You can simply use it as q prime and q. So I'm writing x prime comma 0 and x comma tau. So this is the overlap, and this is equal to basically the time evolution function. So this is u of x comma tau semicolon x prime comma 0. And what we did earlier was to derive a path integral representation for this particular overlap. And the path integral representation, if you remember, you just need to write it. The form is the following. What we have written down now is it is an integral over x. So this is the integral over all possible paths. So this is the measure, path integral measure, and it now runs from x prime to 0 and x comma tau. And in the e to the power of I by h bar action part, what we do is, in the action part was L dt. So I now replace all t's by t tildes, and replace, since I have I've already found that when t is equal to 0, t tilde is 0. So I have set t tilde to be equal to 0. This is the lower limit of the integral, which appears in the exponent. And when t is equal to capital T, t tilde is equal to tau, which is nothing but it. So in the exponent, the Lagrangian part, we have the Lagrangian part and we have Lagrangian times dt. So all the t's, I replace them by t tildes. So dt gets replaced by minus I dt tilde from this equation. If you take dt of this side, then it will give you dt is equal to minus I dt tilde. And then I have m by 2 x dot square, but now I write down, so that is dx dt whole square. So I use the chain rule of differentiation and write dx dt as dx dt tilde dt tilde dt, and then whole square of that. And I replace v, which is the function of x, and it is an implicit function of time t because x is a function of time t. So I replace the t by t tilde. So this is the change that I do in the path integral. And if you do that, now you can see that dt tilde dt, you can just straight away figure it out from this expression that I've written down earlier. And you will see that if you carry out, if you put in the value of dt tilde dt here, you will see that this expression boils down to the following expression. It is a path integral over x running from x prime 0 to x comma tau e to the power of minus 1 by h bar. Once again, this I, the imaginary number, has gone away, and it is e to the power of minus 1 by h bar integral 0 to tau dt tilde times this thing, m by 2 dx dt tilde whole square plus v x t tilde. And this thing we can write it down as path integral over x e to the power of minus 1 by h bar s of e. Now you see, we call this as the Euclidean form of the path integral. So our earlier thing was that had a Lorentzian signature because time was a real, even though that was not a relativistic form of path integral, it was non-relativistic. But now we have actually changed the notion, because Lagrangian, you see, this is once again the same Lagrangian, right? But Lagrangian, we know that it is basically kinetic energy minus the potential energy. But when now the fact that we have rotated the time axis, so now the Lagrangian is no longer the kinetic energy minus the potential energy. Rather, it is the kinetic energy plus the potential energy. So that is why it is called the Euclidean form of the path integral, where AC is the Euclidean form of the action or Euclidean action. It is given by integral 0 to tau. This is m/2. I have just written, so here it was dt tilde, but t is a dummy index. So you can actually put a t tilde here. You can put a t tilde here, but it doesn't matter because t is a dummy index, but you can put it over here. So this is basically integral 0 to tau dt tilde and times the kinetic energy plus the potential energy. And this form of the Lagrangian is called the Euclidean Lagrangian, and this form of the action is called the Euclidean action. So this is something very important, because why it is important we shall see below. We now make the connection of path integral formulation in quantum mechanics, or we now make a connection of quantum mechanics with statistical mechanics. So in statistical mechanics, you see that the most important quantity that we are always after is a partition function. So this z is the partition function, and in quantum mechanics, we write down the partition function as trace of e to the power of minus beta h hat operator. So this is the definition of the partition function in quantum mechanics. And in order to get a nice expression for this, what you do is you just evaluate the trace. So you can take any basis, the nicest basis that in this case will be the eigenstate basis of the Hamiltonian operator, because we know that the k-tens are the eigenstates of the Hamiltonian operator. So you evaluate the trace in this basis. So if you do that evaluation, you will get summation over n Brian e to the power of minus beta h hat operator k10. So this is the formula for the trace. Now once again h hat acting on k10 will give you en. So I will get the factor of e to the power of minus beta en. E to the power of minus beta en goes outside, and then it becomes overlap of k10 Brian, this k10 and Brian, and that is equal to 1. And therefore the partition function becomes simply summation over n e to the power of minus beta en. We exploit this fact that now we exploit the fact that the trace is invariant under a unitary change of basis. So it doesn't matter in which basis we evaluate the trace, right? You can evaluate it in any basis. And so what we do is we switch to the x basis, the position basis, and write the trace of this, write the trace in the following way. So the partition function now can be written as, so in the position basis, which is a continuous basis, you can write the trace as e to the power of minus beta h hat operator, and you take the ktex and bra-x, you sandwich it between x, ktex and bra-x, and then integrate over all x from minus infinity to plus infinity. So this is the evaluation of the partition function in the x basis, in the position basis. We already know what this thing is. You can straight away write it down in the Heisenberg representation, and this function is nothing but the time evolution function. In this case, it is from the initial time 0 to a time which is beta h bar. So you can easily figure it out why this is beta h bar, because this particular object that appears here, you can write it down as e to the power of minus 1 by h bar beta h bar Hamiltonian operator sandwiched between ktex and bra-x. And this particular object, now you can treat this as the time. So this is your like tau. So tau is like beta h, and therefore just tau, which is equal to beta h, sits here. So this particular object is nothing but the time evolution function u, which is a function of x comma beta h semicolon x comma 0. Hence, the partition function z that we have here, this is the partition function z. It is nothing but, if you look at this expression carefully, you will see that the partition function is the sum over amplitudes, because now this particular thing can be expressed in the path integral representation that we have already done here. We have already expressed this kind of a quantity in a path integral representation. So now what happens in the partition function, in the u function appearing in the expression of the partition function, is that instead of x prime, you have a x sitting here, and instead of this tau is basically beta h bar. So these initial conditions, so these conditions, that is why I keep on mentioning that this is very important. This writing of the lower limit and the upper limit in a path integral is very important. Now this x prime becomes x comma 0, and this becomes x comma beta h bar. So this is very important. So now the interpretation comes readily. You can see that the partition function z is the sum over amplitudes to go from the point x back to the point x in imaginary time, tau is equal to beta h bar. So that now the interpretation is very simple. So you see that this is coming from the point, this is starting from the point x and is coming back to the point x in the imaginary time. So it starts from 0 and the imaginary time is beta h bar. So in this time, this is the sum over all amplitudes, and then you integrate over all possible x's, and that will give you the partition function. This is one of the nice ways of looking at the partition function in statistical mechanics, or even in quantum statistical mechanics. And this z beta that you have here, so you can see, you can write this z as a function of beta also, because the beta is a parameter, so this will be a function of the temperature. If you now plug in the formula for this u function in terms of the path integral, you can write down a nice expression for the partition function in terms of the path integral, and that can be written as z function of beta. Beta is basically 1 by kBt. It is basically integral minus infinity to plus infinity dx, and then that function u that appears here, that appeared here in this expression for the partition function, you can just write down the path integral expression for that, and the path integral expression for that actually involves the Euclidean form of the action. Now you see why the Euclidean action is important. So now it involves the Euclidean form of the action. So it comes here, and you can see that this partition function is basically a periodic path integral. Why periodic? Because it starts out from the time t is equal to 0, it ends up at the time t is equal to beta h bar. So this is the imaginary time. It ends up at this point, but it starts out from the same point and ends up at the same point. That is why it is called a periodic path integral. It comes back to the same point. A small remark is in order at this point, but it is a very important remark. The remark is the following: a d plus 1 dimensional Euclidean quantum field theory, or it is actually the same formulation also goes through in the path integral formulation also goes through in quantum field theory. A d plus 1 dimensional Euclidean quantum field theory can be related to a d-dimensional quantum statistical system, since the Euclidean time interval can be consistently identified with beta is equal to 1 by kBt. So at the quantum mechanical level, a quantum mechanics, you can see it as a 0 plus 1 dimensional field theory, right? There are no spatial dimensions, so capital D is equal to 0, but there is a time dimension. So a quantum mechanics can be viewed as a 0 plus 1 dimensional quantum field theory, and such a thing can be identified to a d plus 1 dimensional Euclidean quantum field theory can be identified to a d-dimensional quantum statistical system. So a quantum mechanics can be identified to a 0-dimensional quantum statistical system, since the Euclidean time interval can be consistently identified with beta is equal to 1 by kBt. Because what has happened is the following: quantum mechanics is 0 plus 1 dimensional, so d is 0, and when you make this rotation of the, or when you analytically continue the time to the imaginary time thing, when you do this imaginary time formalism, the time gets identified to the temperature, and therefore the time coordinate is no longer there. So there is no coordinate there involved, and therefore a 0 plus 1 dimensional quantum mechanics thing gets identified to a 0-dimensional statistical mechanics problem. So that is a very, so the important thing to take home lesson is the following: that you can view a quantum mechanical problem as a statistical mechanical problem, and vice versa, as a statistical mechanics problem as a quantum mechanical problem, or more generally a statistical mechanics problem in some dimensions can be viewed as a quantum field theoretical problem in one dimension mode, in one time dimension mode. So that is the connection between a quantum field theory and a statistical mechanical system. So this is some nice connection that comes out from the imaginary time formalism. So it unifies all these things of unifies quantum mechanics, quantum statistical mechanics, quantum field theory, everything. And you can understand that a statistical mechanics problem can be also attacked from a path integral point of view. You can write down a path integral expression for the partition function and try to evaluate it. So this is a nice thing that we learned from the imaginary time formalism. Now I shall come to another important topic. The topic is the following, this topic is important because this is the platform from which we shall actually go to the field theory, the path integral formulation of quantum field theory. So we shall learn how to get time-ordered correlation functions or how to write down time-ordered correlation functions in a path integral approach, or how to get time-ordered correlation functions from a path integral formulation. So let me again recall that. Just a minute. Let me again recall that the transition amplitude, this is the expression that we have already derived. That is the overlap of Qi Ti with Qf at time Tf is given by this expression. I have just put a normalization constant here. It is basically the configuration space path integral. This is the path integral measure, and the lower limit is Qi, Ti, the upper limit is Qf, Tf, which basically says that all paths, it is a sum over all possible paths, but all the paths start from Qi at time Ti and end at Qf at time Tf, and weighted by e to the power of I by h bar times the action, Lagrangian action. Now see, now let us see what do we mean by time-ordered correlation functions. So let us now try to prove one important result. So far we have been talking about these overlaps. Now what happens, let us ask this question, what happens when we put some operator inside this overlaps? So now let us consider a quantity like this. We have a quantity which is q hat, we have an operator which is q hat at time tm, which is sandwiched between qi at time ti and qf at time tf. So this is the object that we want to look at now. So technically this is called as operator insertion. So we are inserting some operator in between these two state gates. So if we do this insertion, the result can be written down in terms of a path integral. The result is nothing but, once again, the normalization constant, path integral over dq. I have no longer written the limits qi, but they are implicitly there. You should always write it down. I have not written it down once again. It is a path integral. The measure is the path integral measure. And then you have q at tm, e to the power of I by h bar action. Now you see this object is no longer an operator, it is a function. So that is the advantage of working with path integrals. You don't need to worry about operators. Everything, all you need to worry are functions. You can play with functions. The operators are no longer there. So let us prove this result. How can we prove this result? It's a simple proof. You take this object, the left hand side, and just insert an identity through the completeness relation. So at the time tm. So what I do is I insert an identity operator through integral dqm bra qf tm q hat at tm, and then I insert this is my insertion, this identity operator insertion along with this integral. Initially the integral was here. I have taken the integral outside. The qm again runs from minus infinity to plus infinity. So I have q hat tm qm tm bra qm tm qi ti. And now q hat at time tm, when it acts on this state, gives you the eigenvalue q at tm. So this eigenvalue comes out, the operator is gone, everything is now, whatever thing you have in this step are functions, ordinary functions. So you have q at tm, and along with the overlaps of qf tm and qm tm, qm tm, qi ti. So this is the expression. Now the next step is integral dqm qtm. You can write this overlap qf tm qm tm qf tf. Sorry, this will be tf. This is something. This will be this. There is an error here. This is. Let me just correct this error. This will be qf. This will be qf. This will be also qf. There is small correction. Sorry for that typo. So now you have qf tf, qm tm, qm tm, qi ti. This overlap, you know that there is a path integral representation. So the path integral representation for this is nothing but it is dqm plus 1 to dqn minus 1 e to the power of I by h bar integral Tm to Tf, because the lower limit is Tm and the final upper limit of time is Tf, L dt. And similarly for this one also, you can write down that it is an integral from q1 to m minus 1, the earlier time interval, which is m minus 1, then e to the power of I by h bar from the lower time Ti to upper time Tf, Tm, L dt. Now this you can combine it nicely. You can write all these integrals separately. So it becomes dqn minus 1 to dqm plus 1. Then dqm comes, then dqm minus 1 to dq1. And then you have q at tm. And then you have this multiplied by e to the power of I by h bar integral Ti to Tf L dt. Because you can combine these two exponents in the following form. This is an integral from Ti to Tm, then Tm to Tf. So you can combine these two exponents to write this as a single exponent running from where the time integral runs from Ti to Tf. So you have this result. And now this particular thing is very simple. This full thing dq1, it is n minus 1 number of integrals, and you know that number of time slices will go to infinity in the limit of the time interval going to 0. So this becomes a path integral measured dq, and this is already there. This is at q at time tm multiplied by e to the power of I by h bar in the action s, which is a functional of q. So what we have shown is that if you put an operator insertion here, then this particular matrix element can now be written in terms of a path integral, and the result is the following. Now you can ask a simple question: what happens when you put two operator insertions? So if you put two operator insertions, now there will be a subtlety. The subtlety is the following: that the operator insertions are at different times, right? So one of the operators may be at an earlier time, and therefore the other operator will be at a later time. So there is an issue, and these two operators may not commute with each other. The operators at different times may not commute with each other, and therefore there is an issue of time ordering. So when there are two or more than two operator insertions, then the issue of time ordering is very important, and therefore the correct object that one needs to look at is the following. This is basically the matrix element of the time ordered thing of or time ordering of these two operators, q hat t1, q hat t2, and matrix element of this sandwiched between qi ti and q at tf. And the result for this is nothing but a very simple result. Once again, you can write it down in terms of a path integral. It is basically path integral dq. Once again, you have these limits. I have not written down the limits. It is q1, q2, it weighted by this e to the power of I by h bar s factor at action. What is q1? Q1 is nothing but q at t1, q2 is nothing but q at t2, and these are ordinary functions. The operatorial character is completely gone. And what is the definition, and what is this time ordering? The time ordering of these two operators, one defined at the position operator defined at time t1, and the position operator at time t2 is defined in the following way. It is the theta function t1 minus t2 q hat t1 q hat t2 plus theta function t2 minus t1 q hat t2 q hat t1. What do we mean by this? The meaning is very simple. It basically means that when t1 is greater than t2, this theta function fires, it is basically equal to 1. And since t1 is greater than t2, this theta function is 0, right? Because this is negative. The argument of this theta function is negative, so this is gone. And this theta, since t1 is greater than t2, this is 1. And then the important thing is that since t1 is greater than t2, the operator which is at the later time, t1 is greater than t2 means t1 is the later time. The operator which is at the later time should be put on the left-hand side of the operator which is at the earlier time. So that is the time ordering. And when t2 is greater than t1, this is off, this is 0. But this theta function fires, this is equal to 1. And then the later time, since t2 is greater than t1, t2 is the later time. Therefore, the operator q hat t2 is the operator at the later time, and therefore it should be put on the left-hand side of the operator, which is at the earlier time. So this is the definition of the time ordering operator. So now I assume I want to prove this result. And how do I prove this result? The proof is very simple. I assume that for the first case, to start with, I assume that t1 is greater than t2. And obviously T2 is greater than Ti, the initial time, and obviously the final time Tf is greater than both T1 and T2. But the important thing is that T1 is greater than T2. If T1 is greater than T2, then this time ordering will simply become Q hat T1 and Q hat T2. So what we need to evaluate is the matrix element of this operator between these two states. So if you evaluate this, once again, you put in the completeness relations, you put in the completeness, the identity operators through the relation dq1 integral over dq1 ket q1 t1 bra q1 t1, and then again another completeness relation involving q2. If you put in the completeness relations, then you will get this expression first. Q hat T1 acting on Q1 T1, this ket Q1 T1 will give you the eigenvalue Q1. And similarly, Q hat T2 acting on this ket Q2 T2 will give you the eigenvalue Q2, where Q1 is nothing but Q1 at time T1 and Q2 is Q2 at time T2. These are short forms, short notations for those objects. So you have this multiplied by these overlaps. The overlaps are the following: QFTF with Q1 T1, Q1 T1 to Q2 T2, Q2 T2 to QI TI. And if you combine, once again, you can break all these overlaps into the path integral forms. You can break these overlaps, and the result will be dq q1 q2 e to the power of I by h bar times the action, which is a functional of q. So we have proved the result at least for T1 greater than T2. You can carry out the same exercise for T2 greater than T1. And in the case when T2 is greater than T1, then this will not fire, this theta function will not fire, this will be equal to 1, and you will be what is needed is to calculate the matrix element of these two operators between the states, between the given states. And if you do that, once again, you will end up with the same result. The result will be the same. And therefore, what you can do is you can combine both the results that we have obtained, both for T1 greater than T2 and T2 greater than T1. And if you combine both the results, you can combine it in this form. You can write that the matrix element of the time order product of these two operators defined at these two times T1 and T2 between these two states QI TI and QF TF is given by the following path integral representation. This is a very important result. The same, all these results that I'm deriving now can be easily applies in case of quantum fields also. So that is why these results are very important, and therefore you should actually have look into these expressions or results very carefully and have some control over these expressions. The next thing that I want to tell you is correlation function. So far, I have been trying to calculate operator insertion, matrix elements of operator insertions between states which are basically base kits. So these are position kits. So I've been trying to calculate matrix elements of these operators and I've tried to written them write it out in terms of path integral representations. But now the next thing that I would like to do is I would like to write down or take the matrix elements or correlation functions in definite states. So probability amplitude for a system in a state psi I h, this is in the Heisenberg representation at time ti, to make a transition to a state psi f h at time pf is given by the following expression. You can see that the system is making, initially it is at psi I in the Heisenberg representation, and it is making a transition to the state psi f, and this is the probability amplitude. And what you can write down is that you can again insert the completeness relation. You can insert QFTF, bra QFTF, integrate over QF, and do the same thing with QI, and you can write this probability amplitude in this form. You can write it down as integral dQF dQi bra psi f ket QFTF, and then this overlap and then this overlap. And now you can write this down as, you can see that QI TI, once again in this overlap Q psi I with psi f, you see that this overlap is made up of this overlap. I think my time is over, but I would just like to take one more minute and finish today's lecture. You can see that this overlap is the familiar overlap that I've been showing you over and over again. This can be written in the path integral representation. I have derived the path integral representation for this overlap. So what you can now do is write down, just plug in the path integral representation for this overlap, and you can write this expression as some normalization constant integral over dqf dqy. This overlap that I have here is the overlap of brass IF with QF TF. This is nothing but the wave function complex conjugated psi f at QF TF. This is the path integral representation, which is basically dq e to the power of I by h bar action, and this is the wave function psi I at qi ti. But now you can, these things, the wave function psi I qi ti at qi ti, this is independent of this q, so you can take it outside the path integral and this, write it down as normalization constant integral over qf qi, the wave function psi f star at qf tf, psi I at qi ti times path integral dq e to the power of I by h bar action, where the wave function is basically get psi bra qt is basically psi qt wave function. So I think it is a nice point for us to stop here today, and I shall continue. I shall pick it up from here in the next lecture. Thank you very much.
Yeah, Sunandan, thank you very
Yes.
much again
Yes.
for a great lecture. And
Thank
there is one comment in the Q&A, but I think that refers to half an hour ago, and I think you might have addressed this already. Otherwise, I would like to invite the participants to raise their hand, and I can press the button to allow them to appear on the screen and ask a question in person. So please, if you want to ask a question, raise your virtual hand or hands, and I will press them. Here we go. Here comes the first question. Hector, please. You're welcome.
Hi, can you hear me?
Yes, I can hear you. Yes.
I just wanted to know, when you rotate time from the real axis and you said you analytically continue to the imaginary side and you identified it with the thermodynamical temperature, is then time subjected to the same dynamics that temperature is? Or how does one understand this kind of a relationship between quantum mechanics and
statistical mechanics? Yes. So this is a nice question. So just get back to this form. So let me just go back a few slides back. So if you notice carefully, you just look at the slide where I've talked about this connection with statistical mechanics. So the partition function is now in statistical mechanics. You can write it down in this is in quantum statistical mechanics. You can write it down as trace of e to the power of this operator, e to the power of minus beta h hat. And beta is basically, I think I have not written, I should have written down. Let me just write it down at this point. Just a moment. So beta is basically 1 by Boltzmann constant times temperature. I think I wrote it down later, but let me write it down here also. So beta is basically 1 by kBT, Boltzmann constant times the temperature, absolute temperature. So this is, so if you expand, if you calculate this trace, then what you will get is summation over n e to the power of minus beta en. So this is the standard expression that all of us know in statistical mechanics, in classical mechanics, statistical mechanics, as well as quantum statistical mechanics. So this is something standard. So now let us go back a few slides back. So if you notice this particular slide from where I started this analytically continuing the time axis to this particular to the imaginary time axis. So if you notice carefully what is happening, what I'm doing is that you just look at the expression. To start with, you look at the expression for the transition amplitude in the path integral representation, in the configuration form of the path integral representation. Just look at that expression. And in that expression, what I'm trying to do is I'm just setting t to be equal to minus I t tilde. So I'm just rotating my time axis. That is what I'm doing. But when I'm in the process of rotating the time axis, what is happening is the following. You will see that the path integral representation, the transition amplitude that we have been talking about, now takes a different form. You will see that the transition amplitude has boiled down to the following form. So this I is no longer here. It is not sitting here anymore. It is completely gone. So in the partition function, now if you just recall the form of the partition function, it is an exponentially decaying function. It is e to the power of minus beta en. So it is an exponential. It is not an oscillatory function. The in the ordinary form of the path transition amplitude, where we wrote it down in the configuration for space path integral representation, it was e to the power of I by h bar action s. So there is a I is complex number sitting there. So it is some, so it is an oscillatory kind of a function, e to the power of is. That is oscillated, but the part in the partition function, the thing that is sitting in the sum end, it is e to the power of minus beta en. So it is an exponentially decaying function. Now, in this process, in the imaginary time formalism, in the process of analytically continuing the time axis to the imaginary time axis, what you will find is that you have actually got rid of the I of the complex number completely, and now this is an exponentially decaying kind of a function. So this is it is like e to the power of minus beta h beta en kind of a thing. So it is, you can see it from this form. It is e to the power of minus 1 by h bar ac, where ac is the Euclidean form of the action. And now we come back to the partition expression for the partition function. When I wrote it down in this form, you can evaluate the trace in any basis. So now I go to the position basis, because the trace is invariant under change of basis, under a unitary change of basis. So if you go to this position basis, which is a continuous eigenbasis, if you go to this basis, you will see that this particular function is basically this evolution function. And we have already derived a form. And the important thing is that this evolution operator, this is, once again, this I is missing. This is not an oscillatory kind of an operator, rather than it is an exponentially decaying kind of an operator. And this function, this evolution function, you see that this is x comma beta h bar semicolon x comma 0. Now your question that where is this temperature identification coming in? The temperature identification, you see that we are actually identifying the time with beta. So it is not, time is not getting identified as proportional to the temperature, but rather it is proportional to the inverse of temperature, because it is beta. So you are identifying T to be equal to beta h bar, but beta goes as 1 by T. So we are identifying, when you are analytically continuing the time axis to the from the real time to the imaginary time, then what you are doing is you are actually identifying the imaginary time with beta h bar, where beta is basically 1 by kBt. There comes the connection of the imaginary time with the temperature. There comes the connection of time temperature relationship. So that is the way you make connection with the time, with quantum mechanics and statistical mechanics. And in the process, what we have done is that in quantum mechanics, as I have already told you, that it is a 0 plus 1 dimensional. So 1 is the time dimension. It is a 0 plus 1 dimensional field theory. But now when you make the connection of quantum mechanics, when you analytically continue the time axis, you have made the connection of time with inverse of temperature, right? And in the process, you have actually got rid of the time nature completely. So you have no time now. So quantum mechanics, which is a 0 plus 1 dimensional quantum field theory, now becomes a 0 dimensional statistical mechanics problem, where you have only the temperature sitting. There is no time. So I hope this more or less answers your question, right? Okay, thanks.
Thank you. Are there further questions by the participants? I don't see. So there's still the raised hand by Hector, but I guess that's sorted unless there is a new one. I don't see any other questions at the moment. Sunandan, so
yes. Thank you.
Everybody is very happy. Yeah.
Okay. Either happy or unhappy, maybe.
Yeah, no. I saw lots of thumbs up and claps up the screen. So I'm sure it will be all right. You see here there are more claps coming up your way. Yeah?
Okay.
So Sunandan, thank you very much.
Thank you.
We will see you again next week. And if you